Hi there. Welcome back to part 9 of my video lecture series introducing the STL. I'm Stefan T. Lauid, Visual C++ Libraries developer, and I'm here today to talk to you about R-value references, which are probably the most complicated C++ OX feature that was added to VC10, Visual Studio 2010. And it comes along with a couple of standard library functions that only occupy a couple lines, so I'm going to devote a whole talk to explaining two functions. These are std_move and std_forward. Which takes an explicit template argument. So these helper functions, what they do, their implementations are very simple, but they're doing something very subtle to the core language, and R-value references themselves can be hard to understand all at once. So let's take a look. They're actually not quite as hard as they seem, and especially the patterns of using them are quite simple. So this feature, R-value references, supports two radically different things. It supports move semantics, and it supports perfect forwarding. One feature, two things that are completely different. The reason why this happens is because R-value references fix a subtle problem in the C++ 9803 core language, something that we couldn't say before. When we gain the ability to say it, then we get these powerful abilities. So I'm going to mostly be covering move semantics today because this makes code more efficient, potentially significantly more efficient by maybe 20%, 2x, 10x, depending on how many unnecessary copies your code was creating. The other thing that R-value references enable perfect forwarding is of extreme interest to generic library developers, people who write templates for a living. Perfect forwarding is absolutely wonderful for them. If I have time, I'll get to it. But if not, if you're just writing your ordinary non-generic code, perfect forwarding, you'll be using perfect forwarding functions like makeshared, but you won't be writing very many of them yourself. Move semantics is definitely the first thing that we want to look at. So first, let me talk about references in general. So R-value references, they are the new kind of references. The old references are called L-value references. Okay. And what these are, they refer to L values and R values, which are things, ideas in the core language. And because we didn't have the ability in C++ 9803 to distinguish clearly between L values and R values, if you're an old programmer like me, these concepts can be really confusing at first. Like, what's an L value? What's an R value? What is this thing? Well, the first thing is that they have horrible names. I mean, the names are terrible. But we're stuck with the names. If we tried to invent new terminology, it'd just be confusing. So we're going to stick with the names. Originally, this meant something like left and right. If you've heard of that, put that out of your mind. That's actually not an ideal way to think about L values versus R values anymore. The correct way to think about them is persistent names for objects versus temporaries. So an L value is something that has a name. And an R value is something that doesn't. Okay. So the thing to remember is that L values versus R values, they apply to expressions. An expression like x or y plus z or array bracket 5 bracket, these expressions can be L values or R values. Expressions can refer to objects, but the objects themselves aren't inherently L values or R values. It can be confusing if you don't keep that in mind. So expressions that are L values, these things have names. They are persistent names for things that you can refer to over and over. So the simplest L value is something like x, some identifier. Or if I have a pointer p, if I dereference that pointer, I can dereference it over and over and manipulate that object over and over. I could say, p arrow member or whatever I like. If I have an array, r, and I ask for its fifth element, I can say that over and over and repeatedly access the fifth element. So if I have a name for a thing, then that expression is an L value. R values are temporaries, things that don't have names. Integer literals are like this. So if I have the number 1729, that's not an object. It doesn't live anywhere in memory. It's just a number. It doesn't have a persistent location in memory. Or if I have a couple strings, s and t, or maybe x plus y, and I ask for x plus y, then this is a stood string if my source is x and y are strings. It's an object that lives in memory, but it's a temporary. It's going to be destroyed as soon as I hit the semicolon at the end of my full expression. So because this thing is a temporary and it's about to be destroyed, it's considered an R value. If you want an even clearer way to distinguish these things, ask, can I take its address? If you could write address x, or address any expression, then yes, it's an L value. So I know that I can write address x, so yes, it's an L value. Or if I dereference a pointer, I can immediately take its address, so it's an L value. It doesn't matter how silly it would be if you wrote address expression, as long as you could write it, then that expression is an L value. Or I could take the address of the fifth element of an array. Whereas, can I take the address of an integer literal? No, I can't. So that's an R value. Or could I take the address of the result of concatenating a couple of strings? No, I can't. And you'll get a compiler error if you try to. So because I can't take the address of things, if address expression is invalid, then I know I'm looking at an R value. This is clearer than the old way of distinguishing L values and R values, which was to ask whether they could be on the left or right side of an assignment. Forget that I said that. That's not a good way to distinguish these things because of consonants. Whereas, could I take the address of it? That's a very clear way to distinguish. So, in summary, L values names, R values temporaries. What good does that do us? Well, now let's think about references. So, here I'm assuming that you've used C++, so you're familiar with the concept of a reference. So these references that you know, they're still good. This reference, if I write something like int ref r, okay, this is now known as an L value reference. They behave just like they used to. They're the old, traditional references. So think about what a reference is. References are actually one of the hardest things to learn when you're doing C++ for the first time, because there's many ways to think about them. One way that is not particularly helpful here is to think of them as auto-dereferencing pointers. Don't think of them like that. The best way to think about a reference is that it's a name for a thing. It's not a thing itself. So if I have an int ref r, maybe I have an int x here, and I bind the reference r to x, then r is another name for x. So if I take the address of r, that's the same as the address of x. Or if I assign through r, I'm assigning to x. I can't write to a reference itself. I can't rebind a reference. It's only a name for something else that lives somewhere. Or if I have a constant ref, maybe I have a function foo taking const int ref c, and if I call foo with x, then this reference c is bound to x. It's not an entity in its own right. So I can take the address of c, and I've got a const pointer to x. Or I could print out c, and that will print out whatever x currently is. The reference isn't an object it's not an object in its own right. It's just a name for a thing. I can bind const L value references to temporaries. So given this, I can also call something like foo of 5 plus 6. This is definitely a temporary. It's two literals added together. But I can, for the duration of the call to foo, bind that reference to 5 plus 6. So L value references, we know how they work. R value references are new. So if I have an R value reference, okay, now I'm going to use string as an example. Okay, I could say, and this is only for the purposes of exposition. This is not something real that you would write. You could write it, but you should not write this sort of thing. I could say string ref, and this would be R value reference, equals, if I've got a couple strings, s plus t. So we know that s plus t is, actually, let me show you the other way that I could write this. Okay. So in this case, I've got a couple stood strings, and I'm concatenating them together, so I get a temporary. This is a very obvious example of a temporary. We know that in C++ 9803, I can bind this temporary to a const L value reference. And what this does is it prolongs the life of the temporary. Temporaries ordinarily are destroyed at the end of the full expression where they live, so they die at the semicolon. However, if I bind a temporary to a const L value reference, that temporary's life is prolonged for as long as CR remains in scope. As soon as I end the scope and CR goes out of scope, then this temporary will be destroyed. But for as long as CR sticks around, I can refer to it over and over. This is one of the ways, really the only way, to prolong a temporary's life. Now, in C++ 9803, if I have a temporary, okay, maybe temporary of type T, I can bind it, yes, to a const tref. This is totally cool, because this const tref only promises to observe the temporary. And I know that I can look at a temporary. However, no, I cannot bind it to a modifiable tref. This is forbidden by the standard C++ 9803 and C++ OX for a very good reason. If I were able to bind modifiable references to temporaries, well, what if I am passing these temporaries to a function that wants to modify through the reference? Such modifications will be instantly lost as soon as that temporary is destroyed. And we know temporaries evaporate very quickly. So allowing temporaries to bind to modifiable references would be an insanely bad idea. That's why it's prohibited by the standard. Now, at this point, I would mention that Visual Studio permits this as an extension. This is what I call the evil extension. It's a very bad idea. Fortunately, it does trigger a warning at warning level at least 4, possibly higher. But if you compile with warning 4, as you should, you'll get a warning if this evil extension is ever activated. If it ever fires, fix your code. Never bind temporaries to modifiable L value references. Very, very bad. So I know that I can write this. Now, R value references are special. What an R value reference is it behaves just like an L value reference with a few exceptions. One of the exceptions is that it can bind to R values specifically, and it never binds to L values. What that means is if I have an R value reference, and how that's written is with 2 ampersands, I pronounce it ref. This can bind to a temporary, and because it's saying that it's binding to a temporary, I don't have that const rule. So I can bind a modifiable R value reference to an R value. This is totally cool. I could then modify RR if I wanted. Like I said, this code is not really realistic. I would never want to write such a thing. But I'm just demonstrating that I can do something with R value references that I could not do with L value references. So let's take a look at some real code now. Okay, so why would I want to do such a thing? Well, let's imagine a class remote integer. Okay, and this remote integer is very simple. It has a data member int pointer m_p. So I've got a remote integer. This is highly unrealistic. It's just sort of an example of a class that stores dynamically allocated memory. It's got an m_p that points to some int somewhere, contains some completely random number. Now, I know that if I have a copy of remote integer, so here I've got a copy constructor. Let me show you here. Okay, if I want to make a copy of my remote integer, maybe this is RI1, and if I construct another remote integer, I'm just abbreviating RI2, as a copy of RI1, what I have to do is I've got RI2 over here. I need to copy my memory over, so I'm going to make another dynamic memory allocation, copy the value of the integer here, and now I've got a separate pointer. So now these have completely separate lifetimes. I can destroy RI1, and RI2 separate copy remains. Now, imagine what happens when you have copy constructors like this. And I write a function, foo, that returns a remote integer. And maybe I have a remote integer. I will omit the type. Well, I can write the type. RI, and I'm going to construct it with some number. Okay, maybe this is going to return, another number like 11. And then if I write RI equals foo, imagine what happens here. So RI starts off containing pointer to its integer. Now, when I call foo, I can get a couple optimizations called the return value optimization and the named return value optimization. Those are great. Those are still implemented in VS 2010. Whenever they happen, they're wonderful. But what they do is they emit certain copies when you return a value. At this point, I don't care about them. What I know is that foo will return a temporary. Whether or not copies are elided along the way, I will get a temporary remote integer because it's being returned by value. So I've got a temporary whose pointer is 11. Points to an 11. Okay. Now, what happens here? When I write this, I know that I'm going to get remote integers operator equal that takes const, and here I will abbreviate, I have to write the whole thing, integer ref other. And here I've got on my laptop code that implements the copy constructor. What this needs to do is it needs to create a new dynamically allocated chunk of memory, copy the number over, and destroy whatever originally contained. This is an assignment operator. Here I've shown you the copy constructor. The assignment operator does what I just said. And importantly, the assignment operator, because it takes a const reference, does not know whether it's being given a temporary that's going to evaporate immediately, or if it's just being given some named value that can be referred to over and over. So I cannot modify the source of the copy because, hey, it could be a named value, and it would be very weird if copying something modified the source. If you know of auto pointer, please forget it. So when I execute operator equal, what this assignment operator will have to do is allocate a new chunk of memory, copy the value 11 into it, destroy whatever the remote integer pointed to, and now we've copied the value into RI, and now the temporary is destroyed. So we destroy this temporary. Look at what we just did. When we returned foo, we allocated a chunk of memory, filled it with 11. When we assigned it, we had to allocate another chunk of memory and assign it with 11, and then we had to destroy the temporary's original chunk of memory. So we have an unnecessary allocation and deallocation when executing this code. This happens all the time. It happens whenever you have a copyable, assignable class in C++, where it's copy constructor and copy assignment operator, allocate memory, or do anything expensive. So std string, std vector, your own classes, there's zillions of examples where just by writing natural code that invokes copy construction and copy assignment, you get these unnecessary allocations and deallocations. That's something we'd like to avoid without destroying C++'s value semantics, which are wonderful. So now, I can write something new, something that I could never write in C++ 9803. If I overload, if I've got remote integer taking const remote integer ref other, this is a copy constructor. If I have, again, remote integer taking remote integer ref other, this is what's known as a move constructor. And what this can do is when you overload between a const L value reference and a modifiable, nothing here, R value reference, you get something very special. Modifiable R values, temporaries, and because they're modifiable, we can write to them, will overload resolution will select this move constructor. This is a move CDOR. Anything else, if it's got a name, if it's an L value, or if it happens to be a const temporary, which is kind of weird, those will select the copy constructor as usual. This is a copy. Move constructor special. Now, the thing about C++ is, yeah, there's this confusing L value, R value thing about expressions, but it enables something extremely powerful. When you have a temporary, when you have an R value, you know something amazing about it. That is the only occurrence of an expression referring to that R value in the whole program. It doesn't have any other names like pointers or references or whatever, L value references, that could refer to the object over and over. So I can modify temporaries and no one else can see the modifications that I perform to them. And I know that temporaries are about to die anyways. So I can do things like steal, literally steal resources from them. In the case that I just showed, where I've got my remote integer with storing a 1729, and then I've got a temporary T that, this is the call to foo, returned an 11. Now I can write a move constructor or a move assignment operator, both using this overloading pattern, and this one will be selected saying, oh, this is a temporary, I'm going to bind my modifiable R value reference to it, and because I've overloaded like this, I know that I can modify that temporary and no one else can see. And because the temporary is about to be destroyed, I can do things like null it out, which ordinarily I could never do. So what I can do is I can make my assignment operator destroy the old contents of my remote integer and perform just a pointer assignment. I can make this remote integer point to this 11. I can null out this guy, so null putter. No extra allocation, no extra deallocation. When the temporary's destructor runs, it says, oh, I've got a null putter, I'm just not going to do anything. We've gained efficiency, and the best part is we did not have to modify the code that said Ri equals foo. Now, think about what happened here. The C++ core language compilers already knew that the result of a function call was an R value. It's a temporary. We don't have to modify this because the compiler already knows that the temporary is about to be destroyed. All we need is the ability to write in the class, here's something special to do when the source is a temporary that's about to be destroyed, and will automatically be picked up by expressions like this. If you're using objects with the STL, the STL has been modified to use move semantics whenever it can. So if you have a vector of remote integers and that vector undergoes reallocation, we saw back in part 1 that when a vector reallocates, it has to copy all of its elements from the old memory block to the new memory block. Well, that old memory block is about to be destroyed. Why copy stuff if you have to? Now, std_vector, if it can, if it sees a move constructor, will invoke it and will move your resources from that old memory block to the new memory block. So what that means is efficiency. Move constructors enable wonderful efficiency. All you get is just pointer twiddling instead of allocating and deallocating. So what does it look like? Here I've got this remote integer. I've got a copy constructor, looks very familiar. What does a move constructor look like? Well, we've seen that I have to overload based on const L value ref versus modifiable R value ref. The one that takes an R value knows that its source is a temporary that can be modified. So I can take the other remote integer's pointer, copy it into my pointer, and then I can null out the other pointer, which will make its destructor do nothing, because I know that no one else can be looking at that. I'm not going to null out something that someone could repeatedly refer to, which would be extremely bad. Similarly, in my assignment operator, here I've got a swap that can simply swap two remote integers. If I am doing a copy assignment, well, this is one of the ways I can write a copy assignment operator. I can construct a copy and then swap into place, and then that will destroy my current contents. If I am writing a move assignment operator, one of the ways that I can write it is like this, where I am going to invoke the move constructor, that's what's happening here, and then swap. So what that means is, this is a little confusing. Okay. I'm writing op equal, taking remote integer ref other, and I write remote integer move other, this is special. Here's an occurrence of std move, dot swap with me. Okay, so we've got this object. Maybe it's a remote integer pointing to an old value like 1729. We've got the temporary, which is other. It's a reference to a temporary that owns something we want. Okay, the quick and easy way to write the move assignment operator that is completely correct is to write this. What this means is invoke the move constructor and create another temporary. This is totally cool because move constructors are efficient. So this is this temporary here. Move the resource in, null out this, okay, then swap it with this object. This, again, just swaps a couple pointers. This points here. This points here. And then we hit the semicolon, so this temporary is destroyed. So we destroy the old value of whatever we pointed to. Writing it like this gives you exception safety, and it allows you to avoid duplicating code. And then you can return this object, and we have moved others' data into this object without allocating a copy. We know a copy is not necessary. And the optimizer can look at all of these just pointer assignments and say, oh, I can do something even better here. Pointer assignments are extremely cheap even if the optimizer doesn't mess with them. So that is one way to write a move constructor and move assignment operator. And if I debug into this, I can show you what happens. So here I've got a couple remote integers, A, constructed with 8, another one B, constructed with 10. I invoke a function called square that's going to return by value a new remote integer. We saw that this would ordinarily trigger unnecessary copies if I went and assigned it into B. Now I expect to get a move assignment. So if I compile and run, here we go. I am about to step into this assignment. I've already printed out 8 and 10. After this, I expect to see 64. I'm going to step in here. I'm going to call square. I know it's going to return a new remote integer by value, so I'm just going to step out of it. I'm going to step back in again. I want to hit the assignment operator. So here, I've selected something new that I could not write in C++ 9803. This is the assignment operator taking a modifiable R value reference. And what it can do is, this is going to move construct that temporary. I'm going to step into std move. I'll explain what that does in a bit. I'll step right back out. We don't want to see what that does. Then step in again. And this invokes the move constructor. I've implemented the move assignment operator in terms of the move constructor. Again, it takes a modifiable R value reference, and it can just do a pointer assignment. So it's going to copy the other pointer into this pointer, this arrow m underscore p, and then null out the other guys m underscore p. And then I'm going to execute a swap. Of course, swap can just swap my internal pointers. I have to call std swap here explicitly because otherwise I would select the member function. That does not do what I want. So I'm going to swap the two pointers, and then I can return this. So that just does what I scribbled on the whiteboard. And I have done no unnecessary allocation or deallocation. If I snipped out this move constructor move assignment operator, I would have no choice but to invoke the copy assignment operator, which would perform redundant copying of temporary that I don't want. So that is great. I have made my code more efficient, and as soon as I step out of all of this and I can see what it prints 60, here we go, print 64. So I have made my code more efficient without affecting its semantics. And all that I've done is add a couple functions, constructors and assignment operators, to my class, and they'll automatically be picked up. Now, what did move do? So imagine that I'm inside operator equal, and I refer to other. And if I said remote integer of other, what did I just explain about L values versus R values? If it has a name, it's an L value. If it has no name, it's an R value. We know that other is bound somewhere to an R value. That's how R value references work. But for the duration of the function call to operator equal, if I say other has a name. L valueness versus R valueness applies to expressions, not to objects. We know that other is bound to an R value, but the expression other itself is an L value. So if I just write plain other, this is an L value. It's very easy to forget this. Now, if I were to construct a remote integer from other, what would this select? Other has a name. So this would select a copy constructor. That's not what I want. I'm writing a move assignment operator. I want a move constructor to be invoked. So somehow I need to start with something that has a name and say, wait, I know that it's really bound to an R value. I want to treat it as a temporary. This is where the function std move comes in. What std move does is it takes an object or a reference and returns an R value reference to it. It converts L values into R values. So if I write move other, this is once again an R value. I have restored the R value-ness. Then I can construct a remote integer from that, and that will invoke a move construction, which is exactly what I want. So you need to use std move whenever you want to convert L values and R values, and the most common place to use them is when implementing move constructors and move assignment operators. It's also possible, if you're just writing ordinary code, to look at that code and say, oh, I am working with maybe some string S. I filled it with stuff. I'm going to then maybe push it back into a vector. And I know that afterwards I'm not going to do anything with S. So you the programmer, can see this. Now, if you just wrote v pushback s, pushback would have no choice but to copy that string into the vector because the source is an L value. Maybe you are going to refer to s later, but if you know that you aren't, you can write move s. What this will do is convert s into an R value and move its contents into the vector, making it more efficient. But afterwards, you cannot refer to s because s has been moved from. It contains garbage. Or it's empty, or it's somehow secretly modified. So move is the moral equivalent of a cast. It's saying, I know better than you do, compiler. I know that this thing is either really referring to a temporary that I know is going to be immediately destroyed, or I can guarantee to you that I'm not going to refer to this anymore. So don't just arbitrarily sprinkle move throughout your code. That is going to lead to bugs. Use it in a very targeted manner. And it's safer to not use it at all. So only use it when you know what you're doing. The other thing to know about R-value references is that you should only use them in the move semantics and perfect forwarding patterns. The thing that I've seen programmers do when they get a hold of R-value references is that they start to go a little crazy because they're so powerful. They start saying, oh, I'm going to have R-value reference data members. I'm going to have R-value reference local variables. I'm going to have R-value reference return values. Then they write code like this. If you write something like x ref blah, this is bad. Don't write it. Disclaimer. If I say something like xx, do things to x, and then return something like move x, people write this. I'm very surprised. Don't write it. What this does is you have a local variable x, and you return a R-value reference to it. Now, if you have been programming C++ for any length of time, you know that if you try to write this, this is bad. You can't have a local variable and then return a reference to it because that local variable is destroyed right here. So you'll get a dangling reference, a reference to an object that no longer exists. Any attempt to use it will be invalid. You'll get undefined behavior. R-value references are the exact same way. You can't return an R-value reference to a local variable and expect that the local variable will survive. It will still be destroyed here. So don't write this sort of code. Do not write functions that return R-value references. Not as return types, not as local variables, not as data members. They can be used by experts. In fact, if you look at what std move and std forward do, they use R-value references like that. But they have been constructed so that they're not returning dangling references. If you are not an expert, if you can't read the standard, which is very complicated when it comes to the core language, and see everything that it's talking about, if you don't know all of the details of overload resolution and reference initialization and template argument deduction, please do not use R-value references outside of the move semantics and perfect forwarding idioms. If you restrict yourself to just writing move constructors and move assignment operators and using std move and std forward in these very well-known patterns, you will be safe. If you start sprinkling R-value references everywhere, you're going to get bugs. Even the standardization committee ran into this. These are the experts who developed the standard, but it's very easy to get into trouble if you use R-value references outside of these patterns. What they had done was in strings operator plus, they made it return an R-value reference. What they had done, and again, this was bad, operator plus, if it takes something like a const string ref, and then a string ref. Okay. They added extra operator pluses, taking R-value references. This was totally cool, so that they could move data around. But then the mistake that they committed was to have some of these operator pluses return R-value references. This ended up, and I won't show you how, but it could allow code that previously worked in C++ 9803 to get a reference to a destroyed temporary. Extremely bad. They fixed this, and we implemented this fix in VC10, so this never shipped ever, except in betas, to return by value as before. It's still efficient because it's taking an R-value reference parameter. It's just returning by value. So this is now good. So don't use R-value references outside of the move semantics and perfect forwarding idioms. One of the things I want to show you is a way to write even less code when implementing assignment operators. So here I've shown you a couple of assignment operators that do this either copy or move and then swap trick. It turns out that these can be unified into what I call the unified assignment operator that allows you to do both of these with a single function. So let me nuke both of these and restore this code here. This is the exact same effect. Once IntelliSense catches up, it will stop graying that out. There we go. And if I run this, if I step in here into this square call, then I'll call square, and now I'm executing this universal assignment operator. What this does is, if you look at it, it is, let me erase some of this. Okay, I've got op equal taking, in the form of this, is it takes by value, this is totally cool, a remote integer, other. Okay. And then it says other.swap deref this. Very, very simple to write. All you have to do is copy and paste this sort of thing and then change the type names. Of course, you have to write a swap. Swap is easy to implement. This unified or universal assignment operator is both a move and a copy. So if the source is a temporary, then what will happen is that the move CDOR will be invoked. Because we're taking this by value, so we need to construct a remote integer here. So if the source is a temporary, then we know that if we've written the remote integer ref move CDOR, that temporary will undergo a move CDOR and we'll get other, and then we simply swap it in place. Same effect. And we didn't have to write std move. If the source was named, if it's an L value, then what we're going to do is we're going to copy it into this value parameter other, so copy CDOR, and then we swap it into place. So just by writing the move constructor and copy constructor, and then by taking it by value here, we can invoke them without saying move at all, and then we simply swap them in place. It is as efficient as writing them out by hand, and it is easier, you write less code, and you don't even have the danger of forgetting std move. Because if you forget a std move, it won't make your code explode or anything, you'll just get a copy where you wanted to move, so it's less efficient. In this case, if you write your code like this, you get both of them for free, which is very nice. It looks a little strange when you first saw it. When I first saw it, I was like, oh, I don't think that's very cool. But then I realized that it's doing 2 for 1, and it removes the danger of forgetting std move. So that's great. That's the unified assignment operator. And of course, writing a swap is always very easy. Usually you just swap its components. Now, you write this sort of code when you have a direct resource manager, something that is newing up things, or it's got handles, or other things that are expensive to copy around. The other sort of class that you run into is a class, and let me remove some of this code. Still running, yes it is. So I'm going to get rid of this int main, goodbye. I could have a class like remote point here. So remote point itself doesn't do any newing of resources, but it has data members, in this case remote integers, that do. This is extremely common. If you have classes that contain std strings, or std vectors, or other, maybe your own classes that do dynamic allocation, then these could also benefit from move constructors and move assignment operators. Thing to know is that in VC10, Visual Studio 2010, move constructors and move assignment operators are never, ever, ever generated by the compiler for you. You'll get copy constructors and copy assignment operators as always, using the normal rules. But you must explicitly write out by hand move constructors and move assignment operators if you want them. There have been changes to the working paper to implicitly generate moves in some cases. It's not quite clear whether those are going to be retained in the final C++OX standard or removed again from the working paper. But in either event, you can ignore that ongoing discussion. Right now in VC10, you never get implicitly generated moves. You've got to write them by hand. So if I have a class containing a std vector or a remote integer, and I want a move, then I'll need to write a move constructor and a move assignment operator. And these implement member-wise moves. These are very simple because we just need to move all of our data members. So here I've got a move constructor, and taking a remote point ref other, I've got an implicitly generated copy constructor, so I'm not even going to write that in my source. In the move constructor, I need to do a member-wise move, so I need to move other.mx into my mx and move other.my into my my. We know that named R value references are L values, so I need stood move if I want to move their guts. So that's why I call move here twice. I can write a move assignment operator that does member-wise move here, and this is very simple to write. I could also write that unified assignment operator if I wanted. I would need a swap, which I haven't added here. But when it's member-wise, it's quite simple. This is also, as long as it's purely a member-wise move, it's exception safe. It offers the strong guarantee, and it also that actually may not be quite correct in the case of throwing moves. Maybe I do want the unified assignment operator here. But in any event, it's quite simple to write. And I won't even bother to execute this code because you know what it's going to do. If I have a function returning a remote point by value, and I assign it into a remote point, well, a function call returning by value, that's an R value. It's a temporary. And so my move constructor will be invoked, my move assignment operator will be invoked. That'll do a member-wise move of my remote integers, and I've seen what's happened there. As I mentioned, in VS 2010, the standard library has been rewritten to take advantage of move semantics. So classes like vector and string have gained move constructors and move assignment operators. So they are already movable. If you just compile with 2010, your code becomes faster for free. Isn't that awesome? Also, classes like vector take advantage of move semantics. So if you grant your classes move constructors and move assignment operators and use them with stood vector of t, where t is your type, then vector will start moving them around for greater efficiency. So it's both sides of the coin. It's providing, the STL is providing move constructors, and it's taking advantage of move constructors and assignment operators whenever it can. Looks like I don't have time to go into perfect forwarding, but if you do a search for my VC blog post about R value references, I have an example there of perfect forwarding. Now, a word about that post. That was written back during the Visual Studio 2010 CDP. The timeline kind of looks like this, where we have the VC10 CDP, we had Beta 1, we had Beta 2, I believe there was an RC in there, that sounds about right, and then we had VC10 RDM. Okay. I wrote this blog post about R value references all the way back in the Community Technology Preview, a pre-beta beta, kind of an alpha. And at this time, we hadn't even checked into the shipping branch the standard library changes for stood move and stood forward. So in this blog post, I had to write my own capital move and capital forward because I knew the standard library machinery was coming, but it wasn't quite there yet. So you'll see that there. The other thing is that here, the committee changed the rules on us. Back here, we had R value references V1, as I call it. And in Beta 2 and beyond, we have R value references V2. The problem is that I wrote my blog post here. So my blog post describes R value references V1, which is not what you have in VC10 RDM. The rules have changed, and I have not yet had a chance to rewrite that post. So the post is valuable if you want to learn about L values and R values, but most of my examples either don't compile or they have different meanings. The change that happened here, it was on the horizon when I wrote my post, was that back in R value references V1, if I had a R value reference like xrefref, this was willing to bind to L values. It didn't want to. Overload resolution would prefer to have L value reference be selected. But if there was no other choice, an R value reference would bind to an L value. It was later realized by the experts in the standardization committee that this is a very bad idea. Certain things could cause this to happen when you didn't want it to, and R value references are used to steal resources. We just showed how move constructors and assignment operators could null out pointers and do other stuff. We don't want that happening to L values. So in R value references V2, if you have an R value reference, this will never, ever, ever bind to an L value. Will not, ever, ever. It will only bind to R values. So you get the safety in VC10 RDM. The only reason I have to explain it is because if you look at this blog post that I wrote back during the CDP, it describes R value references V1. As soon as I get a chance, I'll try to rewrite it and explain R value references V2. But until then, you've got this video, and there's also MSDN documentation that talks about both moving forward. My challenge for you is to take a look at your code, upgrade to Visual Studio 2010, and look for any occurrences where you've got classes that contain things like std strings, std vectors, or things that dynamically allocate memory, and start giving them move constructors and move assignment operators. It will make your code more efficient, and you won't have to resort to contortions like binding temporaries to const references in order to avoid copies. The language and the standard library together will help you avoid copies and generate the most efficient possible code. So, see you next time.